Hi, everybody. Welcome to week 9. Hope that everyone's doing well. It's your 3 favorite chemistry teachers back together again with Miss Ashburn and Miss O'Reilly. Today, we're going to kind of step away from nuclear. I know we've been doing that for the last couple of weeks, and we're going to head into gas laws. Now, you're pretty lucky because if we were in school, we'd be doing a lot of math, but today we're going to be doing a lot of qualitative things with the gas laws. So don't worry about that. So today's objective is that we are going to learn a little bit where you're going to be able to state and explain the kinetic molecular theory, and you're going to be able to use it to describe relationships between several variables, including pressure, volume, and temperature of a gas sample. The middle bullet should make feel like deja vu that name Avogadro is coming back. We haven't seen his name for quite a while. And then finally, we're going to describe the behavior of an ideal gas. So I'm going to throw it to Miss O'Reilly to talk a little bit about kinetic molecular theory.
Nope,
I lied.
pressure.
Sorry.
So first, we're going to be talking a little bit about pressure today. So let's just look at what is pressure. So when we refer to pressure, we're referring to the force that's applied for a given space or a certain surface area where that force is being applied. So we use units like millimeters of mercury, pounds per square inch. You might recognize that from inflating the tires in your car. Kilopascals in atmospheres. The bottom two are the ones you see most often in science. And this wordy definition here is really easily understood by looking at this formula. All it is the words to describe that mathematical relationship. So pressure, it equals the force divided by the surface area. So this example here is what I want you to think about. Compare being stepped on by a stiletto versus an elephant. And you think, whoa, an elephant, I don't want to be stepped on by an elephant. But let me tell you, if you've never been stepped on by a stiletto, it hurts. So this stiletto, the surface area between the little heel and the ball of the foot, part of the heel, the shoe, is a very small surface area. So even though you're just taking the weight of a human, the force due to gravity of a human, and dividing by that little tiny surface area, makes it that has a large amount of pressure. Take into consideration that an elephant has 4 very large feet, so covers a lot bigger surface area. Even though that elephant weighs a lot more and has a greater force, the pressure exerted by that is a lot less. We're going to look at a couple examples to help you see the difference here. The first example is who exerts the least pressure. So take a look at the pictures to the right and answer the question. So I hope that you all selected B. The person B exerts the least pressure because even though they're all the same person and have the same weight or force due to gravity, person B has the greatest surface area. They're spreading out all of that force over a greater area and putting less pressure in that space.
In fact, animals use it going on ice. Polar bears, you can actually see polar bears use it. They'll spread out if they're worried about the ice, and some of your ice rescue firefighters, that's how they'll actually try to get to a victim.
And speaking of snow in winter,
woohoo!
Our next question asks about snowshoes. What is the advantage of the snowshoes to walk across a snow-covered field? So I hope you selected that it increases the surface area and causes you to put less pressure on the snow. What that'll do is it'll allow you to walk on top, like on the surface of the snow without sinking down into it. Whereas if you were just wearing the plain pair of boots, your feet would exert more pressure and you would fall right into the snow. You'd sink deep into the snow.
Okay.
And now we're going to send it to Miss Ashburn.
There you go. So I'm going to be talking about the kinetic molecular theory. And really what this is it explains the behavior of particles. All right. So if you think about it, right, you have laws that state fact, theories kind of help explain behavior. So you have gases, have tiny particles. They're very, very small. And they're spread out so much that they really, right, they're not bumping into each other. There's a large distance between the particles. They're in constant random motion, and they hit the sides of their container. So even at the bottom there where you see the difference between the solid, the liquid, and the gas particles, solids tightly together, only vibrate, they have low energy. Liquids, little more energy, they're kind of flopping all over the place around each other. Gases, high energy, and they were like, they're flying everywhere. Okay? And the big thing when we look at the kinetic molecular theory and use it to explain it, we're explaining that when they collide with the side of the container, they don't lose any of the energy. So if you took a super ball and you bounced it, each time it bounced, it would bounce up a little less, right? Until it was really just kind of bum, 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 bum along the ground. You have to picture gas particles as always coming back to that same point. They do not lose any of their energy as a result of the collision. So we call that, it's elastic. And at a given temperature, gas molecules have a constant average energy.
Yes.
And that's really what temperature is. It kind of measures the average kinetic energy of particles. So now I'm going to pass it off to Mr. Harf.
Okay, so the first of many laws that we're going to talk about is called Boyle's law, which is a pressure-volume relationship. The one thing that we have to also say here is that the other variables, which would include temperature and the amount of molecules here, are going to remain constant, okay? So it's an inverse relationship, which means that the two variables behave opposite of each other. So if you look at the big diagram on the right, you can see in this diagram that we have a piston. And what's going to happen is that the handle can be pulled up or be pushed down to change how big the space is. Okay, so if you look at the picture on the left, the part of the left is, you're going to see that when the molecules have more space, they're going to be further away from each other. As they're further away from each other, the likelihood of colliding is a lot less. So in a bigger volume, the pressure actually is pretty low. If you move to the right side of the diagram, you're going to notice that the piston was pushed in and the volume became much smaller. Because the volume became much smaller, all those molecules are now more in a smaller space, which means that they're closer together, which means that they're going to probably hit each other more. And when they hit each other more, the pressure is going to go up. So in conclusion, Boyle's law is a pressure-volume relationship, and they go opposite each other. So high pressure, low volume, low pressure, large volume. Okay, and then there's some examples, but I'm going to throw it to Ms. O'Reilly to do another law. I think Charles.
So for Charles's law, we're going to look at temperature and volume. These two variables we're going to look at when all other variables are kept constant. So if the only two variables that are changing are temperature and volume, they will be directly proportional to one another. So that means they behave the same. If one goes up, the other goes up. If one goes down, the other goes down. And you can see that in the diagram to the right. So in this one here, on the left-hand side of the diagram, there's a lower temperature. And remember, temperature is the measure of average kinetic energy. Kinetic means motion. So if they have a lower average kinetic energy, they're going a little slower. So that is going to happen at a smaller volume. They're not going to be pushing on the walls of the container. So this sliding piston here is going to be able to compress. On the opposite side here, we have a higher temperature. Those particles are moving a lot faster and they're pushing on the walls of the container more and causing that piston to rise. So this would only work in an expandable container, one that can grow or shrink. And there's some examples of where this happens on the left-hand side as well. And I'm gonna send it to Miss Ashburn.
All right, Gay-Lussac's law is looking at pressure versus temperature. So I'm just reminder, like we started with Mr. Harfness, that if we're looking at pressure and temperature, we're keeping the other variables constant. So volume's not changing. These guys, they're directly proportional, which means they behave like each other. So if one goes up, the other goes up. If one goes down, the other goes down. And this actually, if you think about it, makes sense because temperature is a measure of the average kinetic energy. So if particles have more energy, they're going to bounce off the sides of the container more, so the pressure is higher. Because pressure, when we're looking at gases, is all about the collisions with the container. So if you look at the first piston picture, right, you have low temperature, so they're not moving as fast, so you're going to have lower pressure because you have fewer collisions. In the picture to the right, We have higher temperature, which means higher energy. They're moving faster. They're going to bounce off the wall more. So you're going to have more collisions, which means more pressure.
Okay, so we're going to talk a little bit now about ideal gases. An ideal gas is a gas sample that behaves under all conditions as the kinetic molecular theory predicts. Okay, most gases behave very closely to ideal gases, but they don't obey all the parts, okay, of the kinetic molecular theory. At very high pressures or very low temperatures, real gases do not behave ideally, okay? So if you look at the diagram on the right, it's this kind of a diagram showing you some properties of ideal gases versus some real gases.
Avogadro's law. So now we're looking at the number of particles. So like we said before, when you look at the laws, they're looking at two of the variables and leaving the other ones constant. So when we look at Avogadro's law, which it goes back to Avogadro's number, the mole, how many particles, you'll notice it says 1 mole equals 22.4 liters at STP. And that STP stands for standard temperature and pressure, meaning the temperature and pressure are the two variables that don't change. So we're looking at the relationship between the number of particles and the volume. So it says equal volumes of all gases at the same temperature and pressure contain the same number of molecules. So 1 mole of a gas at STP will always be equal to 22.4 liters.
And so we're just going to review really quick. So the first thing we said was the kinetic molecular theory. Gases have a negligible mass, they're in constant random motion, and they have elastic collisions. We looked at the relationship between pressure and volume. They're inversely proportional. As pressure increases, volume decreases. We looked at the relationship between temperature and volume. As temperature increases, volume increases. That's directly proportional. We looked at the relationship between temperature and pressure, which was also directly proportional. As temperature increases, pressure increases. We looked at the volume of a gas at standard temperature and pressure. All gases at STP have a volume of 22.4 liters in 1 mole. And gases will act like ideal gases except under those extreme conditions. So we hope that this video helped you. You are going to be working with these relationships between the gases, the variables, pressure, temperature, and volume in parts B and C this week. Part B will be some demonstrations that you're going to have to take some notes on, essentially. And part C will be a demonstration where you will have to interpret it and explain what's going on the molecular level. So if you have any questions, feel free to reach out. Google Classroom or email would be happy to help. Have a great week, everyone.
Bye.